We're looking at Chapter 6, Section 6.3, Solve Problems that Involve Exponential Equations. We're going to learn how to rewrite both sides of an exponential equation as powers of the same base, and we're going to convert a radical expression to its exponential form. In order to be able to solve an exponential equation, including a radical, we have to first turn the radical to its exponential form. So let's have a look back at what we've been studying. We've been looking at various polynomial functions and exponential functions and how their graphs and their equations give us some ideas of what their characteristics are. So we look at a constant, and we were looking at the number of x-intercepts, the number of y-intercepts, the end behavior, which is determined by a leading coefficient, the domain, the range, number of turning points, and we could even sketch each one of these. If we're looking at a constant, we have, of course, would be a horizontal line. If we look at a linear graph, we have a increasing linear function or a decreasing linear function. For a quadratic, we have a parabola that would open upwards or a parabola that would open downward. For a cubic, if you have a positive leading coefficient, we would have an N-shaped graph. For a negative leading coefficient, we'd have a backwards N-shaped graph. And of course, an exponential, we have an increasing exponential, or we have a decreasing exponential. And the end behavior for each of those are the same. Let's look back at an exponential function. We have increasing exponential functions. Once again, the end behavior goes from quadrant 2 to quadrant 1. And we know an increasing exponential function when b is greater than 1. Don't forget, a will be our y-intercept, but an increasing function is when b is greater than 1. We would have a decreasing exponential function when the value of b is between 1 and 0. So we can solve exponential functions by graphing the two functions. So for example, if we have 3x is equal to 9, then if we graph y equals 3 to the x, and we graph y equals 9, the intersection point would be the solution. So here we have y equals 9. Here we have y equals 3 to the power of x. And the intersection point where they intersect would be the solution. So x would equal 2. Let's have a look at the rational exponents. A radical expression, when we put it in exponential form, we would have rational exponents. So the square root of 25 would actually be expressed as 25 to the power of 1/2. The cube root of 8 squared, which can also be written as the cube root of 8 squared, is actually 8 to the power of 2/3. And that is, the index will always be the denominator. And so the index here, of course, is 2, although we do not write it there. So keep this in mind when we're solving exponential equations. It's likely that you may have one of the parts of the expression be a radical. So we have to recall the powers of each number when we're doing this. We have the powers of 2. Of course, 2 to the power of 0 equals 1. 2 to the power of 1 is 2. 2 to the power of 2 equals 4. 2 to the power of 3 equals 8, and so on. If we go below that, 2 to the power of -1, it's not -2, it's 1/2. 2 to the power of -2 equals 1/4. 2 to the power of -3 equals 1/8, and so on. When we're looking at the powers of 3, we have the same idea. We have 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. 3 to the -1 is 1/3. 3 to the -2 is 1/9. and 3 to the negative 3. It's 1 over 27. When we're looking at the powers of 4, and you'll see that every second power of 4 is a power of 2. We have 4 to the power of 0 equals 1. 4 to the power of 1 equals 4. 4 to the power of 2 equals 16, which would be the next one in 2. So when we're writing things with powers of 4, we could also write anything with the power of 4 as a power of 2. We have 4 to the negative 1 equals 1/4. 4 to the negative 2 equals 1 over 16, and so on. Let's have a look at the powers of 5. So we have 5 to the power of 0 is equal to 1. 5 to the power of 1, 5. 5 to the power of 2 equal to 25. 5 to the negative 1 is 1 over 5. 5 to the negative 2 is equal to 1 over 25, and so on. So we have to recall these powers when we're solving exponential equations. So when we're looking at exponent properties, there is a couple rules that would help us to solve. The common base rule, which says that if two powers are equal to each other and that they have the same basis, then their exponents must be equal to each other. For example, if 5 to the power of x is equal to 5 to the power of 2, then x must equal 2. And we will use this. This is a very important rule when solving exponential equations. There's a power rule when we have what we called in grade 9 powers of powers. So b to the power of x, all to the power of y, then we would multiply x times y. For example, 2 to the power of 3, all to the power of 4. We multiply 3 times 4, which would give us 2 to the power of 12. So let's use a couple of these properties to help us solve exponential equations. And how we do this, we must change each side of the equal sign to a power with the same base. So we have 6 to the power of x will equal 6 to the power of 3. This will give us, since the bases are the same, x equal to 3. If we look at the next one, we have 3 to the power of x, and we know 1 over 27 can be written as a base of 3 if we go 3 to the negative 3. So that means x would equal negative 3. So we have 2 to the power of x would equal 2 to the negative 2. So x would equal negative 2. So when you look at each side of the equal sign, you must determine what base I could write each power with. These are getting a little bit more complicated here. We have, our bases are 3 and 1 over 81. Now I know 81 can be written as a base of 3, so 1 over 81 must be able to be written as a base of 3 with a negative exponent. And so I have 3 to the 2x will equal 3 to the negative 4, all to the x subtract 1. So I would continue. 3 to the 2x would equal 3 to the negative 4 multiplied by all of x subtract 1. So here, since the bases are the same, we would have 2x should equal negative 4x plus 4. Remember, this 4 uses distributive property is multiplied throughout the whole bracket. So that would give us 2x plus 4x is equal to 4. 6x would equal to 4. X would equal 4/6, or 2/3. Let's look at the next equation. We're looking at bases of 25, 25, and 125. And we have a radical here. So we know there's going to be fractional exponents over on this side. We asked ourselves, what can we write 25 and 125 as a base of? When we continue, we have 5 to the 2 all to the 3x. It's going to equal 125 to the power of 1/2. First, we have 5 to the 6x, which would equal 5 to the 3 all to the 1/2. We have 5 to the 6x, which would equal 5 to the 3 over 2. Now, since the bases are the same, and we have two of the powers equal to each other, then we could say that 6x will equal 3 over 2. So x will give us 1/4. In the next problem, we have the same. We have to think, what could 1/4 and 1/16 be written as the same base? We actually have two options here. 4 can be written as a base of itself, 4 to the power of 1, and that would give 1/4 as 4 to the power of -1. 1/16 would be 4 to the power of -2. We also have 4 can be written as a base of 2. This would be 2 to the power of -2, and this would be 2 to the power of -4. Both options will work, but always be sure that you are correct and that it can be written as those bases. So we have 4 to the -1 all to the x is equal to 4 to the -2 all to the power of 3x subtract 2. This will give us 4 to the -x equals 4 to the -2 multiplied by all of 3x subtract 2. This would give us -x is equal to -6x plus 4. Remember to use the distributive property here. We have -x plus 6x, which would equal 4. 5x equals 4, so x would equal 4/5. And we're going to take it just one more step further here. We're looking at this equation, and it may be a little bit confusing because you're trying to figure out how would you write 3 and 18 as something with the same base. You may think, oh, well, 3 times 6 is 18, so it must be written as a base of 3. Yet, this is not correct. What you have to do in these cases would be isolate the power. We're going to isolate the power. Since the power is being multiplied by 2, we will isolate the power. And so we have 3 to the x plus 2 would equal 18 over 2. And this would give us 3x plus 2 would equal 9. And of course, now we know that 9 can be written as a base of 3. So we have 3x plus 2 to equal 3 to the 2. So x plus 2 would equal 2. X would equal 0. The next example, you're trying to figure out how to write 4, 7, and 57 as the same base. Yet we have to isolate the power. The power is not isolated on its own. So we have not on its own, rather. So to do this, we would have 4 to the 2x subtract 1 would equal 57 plus 7. 4 to the 2x subtract 1 would equal 64. We can write both 4 and 64 as a base of 4. So we have 4 to the 2x subtract 1, which would equal 4 to the 3. So now we have 2x subtract 1 would equal 3. Since the bases are the same, we can use the common base rule. 2x would equal 4. X will equal 4 over 2. X would equal 2. So let's have a look at another complicated example. You could pause the clip now and attempt it on your own. I will continue. We have 3 to the 1/2 all to the 4x, which would equal 3 to the 3 all to the power of x subtract 3. This would give us 3 to the 2x when we multiply 1/2 times 4, which will give us 3 out of x subtract 3. We will be left with 2x will equal 3x plus 9. Don't forget the distributive property. So 2x subtract 3x would equal 9. Minus x would equal 9. So x equals -9. What if we cannot get the same basis? So you're looking and you're trying to figure out, what could I write both 2 and 9 as the same base? Well, if we're doing this by graphing, or let's just try some inspection, I know that 2 to the 1 would equal 2, and I know 2 to the power 4 would equal, 2 to the power of 2 would equal 4, and I know that 2 to the power of 3 would equal 8, and 2 to the power of 4 would equal 16. So 9 falls somewhere in between 8 and 16. Therefore, x is somewhere between 3 and 4. We're going to solve problems like this, where the basis cannot be written, where the equation cannot be written with the same basis. We're going to investigate problems like this in Chapter 7. So in summary, when solving exponential equations, we have to write each side of the equation as a power of the same base, and then equate the exponents to solve for the variable using the common base rule. Be aware that radical expressions will give fractional exponents.